All right, just a recap of yesterday's lesson in case you thought you needed one more extra example. So what we talked about yesterday was the rational zero theorem. So that is finding your P divides Q. Where the numerator is all of the factors of the last term. And the denominator is all the factors of the first term, in this case 1. And then we're going to use Descartes' rule to determine the number of positive and negative real zeros. Now this is in standard form, but we are missing 0x cubed. So the signs would go positive, positive, negative, negative, positive. So that means we have 1, 2 sign changes. So I could have 2 or 0 positive real roots. Plugging in negative x. We get x to the 4th plus 0x cubed minus 6x squared plus 8x plus 24. So 1 sign change. So that means we could have 1 or 0 negative real roots. So following that combination, we can have 2 real positive with 2 imaginary. We could have 4 imaginary. And we could have no negative, because you can't have 1 if it is, we can have 1 negative and or 1 positive. So just taking these and taking the positives, we could start with 1. Coefficients go 1, 0, negative 6, negative 8, 24. One does not work. Negative 24 does in fact work, so that makes us happy. So that means that this factors into x minus 2, leaving you x cubed plus 2x squared minus 2x minus 12. So knowing that this is x cubed plus 2x squared minus 2x minus 12, I could try to find, using synthetic, another number that will go into this. So now you can look at the cubic and you could say, okay, what's my P divides Q for this? since 6 wasn't a factor, or 6 was a factor of the original, since they're all factors of the original, they're all potential factors for this. And again, looking here, we have 1, 2 sign changes. So that means that this still has the potential to have 2 real positive roots. And if you plugged in a negative, same thing, you would have 1 negative change. So that means you could have 1 negative. So looking back through these, I'm going to say, okay, what's 1 plus 2? That's 3. 3 minus 2 minus 12 is not going to be 0, so 1 doesn't work. Now you could have a repeated root, so 2 could work again. So maybe I try 2 again, but I'm going to try 2 with my new factored form. And we see that 2 works again, so we're super happy. So that means that x minus 2, x minus 2, x squared plus 4x plus 6 is my next factored form. So at this point now, we have 2 positive real roots. So we know that this either has to be a imaginary or a negative. So what I would do is use quadratic formula because that's the easiest method for a quadratic, and say that x equals negative b plus or minus the square root b squared minus 4ac all over 2a. And we see that we get 2 imaginaries. So my 2 imaginary roots are negative 2 plus or minus I square roots of 2. And my reals are both at x equals 2, and they are repeated roots. And again, just to make that full connection, if you were to graph this, if you go back and you look at this right here, my leading coefficient is 1. That is positive. This is a quartic. So the leading coefficient is positive. The degree is even. So in terms of end behavior, as x goes to negative infinity and x goes to infinity, f of x is going to infinity for both. So we're ending high. I know 2 is going to be a 0, and because it's a repeated root, it means it's not going to cross. This tells me my y-intercept is 24. So this goes through 0, 24, crosses at 2, and goes back up. Somewhere in here, it's probably going to have another little bump. So maybe here it goes up and then continues again. That would be where your repeated roots are occurring as the complex roots. And if you look on a graphing calculator, I drew the little extra thing on the right side, but it's actually over here on the left. Just kidding. So you can kind of see it right there. Ending high, intercept at 24, and the extra little bump.